Welcome back to our lecture series on the subject Material Science and Metallurgy. This is Dr.L.Bhanu Prakash, working as an associate professor in the Department of Mechanical Engineering at MLR Institute of Technology. In today's lecture, we will talk about copper alloys. In our previous lectures, we have discussed brass and bronze are the two classic alloys of copper. Then in today's lecture, we will talk about the copper nickel alloys, which are called as Cupronickels. So this is an overview of today's presentation. So we talk about, as usual, for all the materials as we have discussed, we have talked about its basic definition. Then we have talked about the composition. In today's lecture also, we talk about the composition of Cupronickels, then the microstructure, then properties, then certain advantages and limitations of the materials and the suitable applications. Then we talk about the manufacturing process, and finally we compare with all the competitive alloys of copper nickel alloys. Finally, we'll summarize our lecture and we look at the key takeaways. So copper nickel alloys with 10 to 30% as a nickel composition that has been considered in the copper. Copper is being the matrix and the nickel is being added as an alloying element. So the weight percentage of nickel that is added is up to 10 to 30%. So in addition to the nickel, we could also see the additions of iron and manganese. Some of the key features of these cupronickel are it will be having a silver appearance, which basically coming from the nickel, which resembles the nickel, and it is known for its outstanding severe corrosion resistance. So particularly with the seawater, it offers greatest corrosion. So instead of going with other stainless steel and other materials, one can utilize this copper nickel alloys because of their excellent seawater corrosion resistance. This is one of the key feature of this material. Then it is having antimicrobial properties, where in the areas of hospital, wherever the touch surfaces are there, they are basically coated with these copper nickel alloys because to eliminate the microbial activities. So this material also acts as an antimicrobial resistance. It offers the greatest antimicrobial resistance as well. So these are some of the key features of cupronickels, copper nickel alloys. If you look at the composition and the grades, so we have 90-10 percentage, 10 where 10% of nickel is being considered in the copper. Then we have 30% nickel, that is called 70-30 copper nickel. Then we have very low nickel variant as well. So these are the three grades that we have it, which is having the serial number as this: C70600 and C71500, 71,000. And if you look at the composition in particular, so copper is close to 90%, as the name itself, it is given as 90-10 copper and nickel. So 88.6% is the copper and 10% is being the nickel, and remaining is the iron. So this is mainly used in general marine applications because of their outstanding seawater resistance, particularly, and so it finds its applications in the marine sectors. Then we have 70-30 copper nickel alloy, so where copper percentage is being 68.5% and nickel is 30%, and remaining is the iron again, which is 1.5 weight percentage of iron. This is suitable for high strength as well as corrosion resistance is required. So in those areas we will be using this material. So it offers both strength as well as corrosion resistance. And then we have very low nickel variant, that grade material also, where even though it is low variant, so it is 21% of nickel is being there, and then 79% is the copper. There is no other alloying agents, so which is basically used in coinage for making the coins. So mostly in the US, we can able to see these coinage applications in the US. So this is also called as US nickels. So iron, which is considered at about 1 to 2 percentages, will significantly enhance its pitting resistance, and manganese, that is been considered for deoxidizing the molten metal. So it will be manganese will help in deoxidization, so it will prevent from the oxide layer. This copper can react with oxygen and can create copper CuO2. So this can be eliminated, and the nickel oxygen also can be eliminated here. So both can be eliminated with the addition of manganese. Whereas iron is being added for increasing the pitting resistance of the overall material. So if you see the microstructure, so we have a single phase alpha solid solution, that is which is having FCC crystal structure at all nickel percentages, so which is having excellent cold workability. So it is a single phase alpha solid solution. Then we have iron manganese, that will be forming the fine precipitants. Iron and manganese both will form as a fine, very small particle precipitates, which basically strengthens without sacrificing the corrosion resistance. So without sacrificing its corrosion resistance properties, the strength can be significantly improved with these precipitates, iron and manganese precipitates. So these two can be observed in the material in microstructures. You see the mechanical properties of these two grades. One is C70600, that is 9010 copper nickel. Then we have 71500, which is if we recall, so that is 7030 copper nickel. So if we compare both of them, the tensile strength is close to 350 MPa, and whereas in this, as the nickel percentage is increasing, so in this nickel is about 30 percentage, whereas here nickel is about 10 percentage. So with the addition of nickel at 10 percentage, this 9010 copper nickel alloy, which is contributing to 350 MPa tensile strength, whereas as the nickel is getting increased in the copper, its tensile strength is also getting improved significantly. In terms of elongation, it is slightly deduction of by 5 percentage reduction with the addition of nickel, as the strength is getting improved and its elongation is getting reduced, because copper is having very good elongation percentage. So the addition of nickel, so it is significantly reducing its elongation, and also it's increasing the hardness value. So it's Vickers hardness, HV Vickers hardness is about 150, and for 9010 it is 100. So one can say that with the addition of nickel, its strength and hardness is increasing, whereas its ductility is slightly reduced. With a compromised ductility, we can improve strength as well as the hardness of the overall material. So that is what it is given. So nickel, with the addition of nickel percentage, strength can be improved, but the cost is dramatically getting increased. So that is, we have to look at it with respect to, we have to make the trade-off between the improvement of strength against the cost. So we have to do this trade-off here. With the increase in nickel percentage, strength is getting increased and cost is also increased. Parallel cost is also dramatically increasing. Then, as we have discussed, it's a corrosion resistance. It's a seawater resistance is very good, pretty good. It forms a protective oxide layer, that is nickel oxides and copper oxides, CuO. Copper oxides and nickel oxides both offers resistance against the corrosion. So it is resistance to biofouling as well. So it prevents from fouling also, biofouling particularly. And with the addition of iron here, this also can prevent the under deposition pitting. So iron, as we have seen in our earlier discussion, so iron, with the addition of iron, we can improve the pitting resistance. So pitting resistance can be improved. So the material can be prevented from under deposit pitting. So it offers significant seawater resistance, and so it finds its applications in marine. Then we have stress corrosion cracking resistance, also SCC resistance. Stress corrosion cracking, so which is immune to the chloride SCC, stress corrosion cracking. So corrosion that causes the stresses that develop stresses, which in turn leads to the cracking in the material. So that one can see it in the stainless steel, but this material is having immune to this, particularly with the chloride based SCC. So with respect to the chloride, so this chlorine again can be present in the water, and if we use uh, materials like stainless steel, which can be affected with the chloride, and it can be damaged eventually over the time. Its durability can be less when compared to, relatively less when compared to these cupronicles. Then it is having galvanic compatibility, cupronicles, which is near Nobel potential. It is near theoretical potential it is having. So it is safe coupling with titanium or copper alloys. So it can be coupled with titanium based alloys or copper based alloys. Then if you look at the applications of these materials, as we have discussed, because of its excellent seawater resistance, which finds its applications in the marine sector, where we'll be using it for condenser tubes and ship hulls. Ship hulls basically, they can be made out of these cupronicles, ship hulls, and also some of the condenser tubes also manufactured using cupronickel, which is C70600, that is 9010 copper nickel, 9010 copper nickel alloy. Then in the power plants we use 7030, that is 7030 copper nickel, which is used in desalination heat exchangers. In the heat exchangers, we'll be using this cupronickel. Then we have coinage, which is low nickel alloys, low nickel cupronickel, which finds applications in US nickels and euro coins. They are manufactured out of cupronickel. Then in the medical sector also it finds its applications, particularly 9010 copper nickel alloy, because of their antimicrobial touch surfaces. These are the sectors we practically finds its applications. So the USS Nautilus, the first nuclear sub, which is used 7030 cupronickel for all seawater systems. The first US Nautilus is being employed with 7030 cupronickel for all seawater systems. If we discuss the manufacturing processes, we'll be going with the melting and casting. So here we do the melting through the induction. Induction means, so induction melting will be done under the inert gas atmospheres, which basically prevents oxidation of nickel here. Then it can be hot worked also, hot rolled at 800 to 900 degrees centigrade, where alpha phase remains stable. So there will be no changes in the microstructure, and eventually there will be no changes in the properties as well. So it can be comfortably hot rolled at 800 to 900 degrees centigrade, where some of the properties can be altered. And it will be cold working is also been possible, and that is been employed with the annealing or refinement of the grains. We will be going with annealing. So cold drawn tubes, which are basically done with the intermediate annealing at 550 to 650 degrees centigrade. So annealing is done at 550 to 650 degrees centigrade, whereas which are basically earlier it is done with a cold working process. Then welding, we do the welding as well. So TIG welding is preferred. So these are the filler wires, copper nickel filler wires. Here copper nickel filler wires will be employed for its welding. So these are some of the manufacturing processes that is being employed to bring the copper nickel based alloys into its engineering applications. Some of the advantages, as we have seen, it finds its unrevealed seawater corrosion resistance, which finds its applications in marine sectors. We have been using it from past 3 decades. It is also having excellent thermal conductivity, which is 50% better than the stainless steel. Because of this reason, it can be employed in heat exchangers and other condenser tubes, and such applications are also welcomed. Then it is non-magnetic in nature, which is very critical in some of the minesweepers and MRI rooms. So in MRI rooms also, we require materials which are non-magnetic in nature. So this Cupronickel is non-magnetic in nature. These are some of the advantages. Due to its advantages, it finds its applications in different engineering sectors, from medical, marine, then thermal, power plant, and such engineering segments, key engineering sectors. However, it does have certain limitations in particular to the cost, where nickel is being one of the expensive materials. Then it is also finds difficulty in machinability because of their gummy chips, because of their ductility, and the chip formation is not that great, and it is always cutting is little tedious, mm, which requires basically very sharp tools to avoid this gummy chips, which does not allow basically the machining process. So these are certain limitations of cupronickel. We have certain special cupronickel alloys for us, where, as we have discussed, we have, in addition to the nickel, you find 2% of iron and 2% of manganese. So we have copper, nickel, iron, manganese alloy C71640 with a grade, where 66% is the copper, 30% nickel, and 2% iron, and 2% remaining 2% is being manganese here. So this has been added with 2% iron and 2% manganese. It it offers superior erosion resistance for high flow seawater. So if we use this cupronickel for tubing applications, where certain seawater is getting flowed, so this material, this specially made alloy, can offer very good resistance against the erosion. So it offers superior erosion resistance for high flow seawater. Then we have another special grade alloy, that is 5% nickel silver. So technically a nickel brass It is called technically it is nickel brass, but often it has been grouped with cupronickel for its color because of their silver appearance. Presumably that is coming from the nickel addition of nickel. So because of its color, it has been often clubbed with or grouped with cupronickel, but basically, typically it is, or technically it is nickel brass. Nickel is being added at 5%. So if we compare cupronickel, particularly 7030 grade cupronickel with stainless steel and titanium in terms of its corrosion resistance and thermal conductivity and cost. So corrosion resistance is the best that it can offer, whereas titanium is the next to it, which is excellent. Titanium is being excellent candidates, and corrosion and 7030 copper nickel is also one of the better. Stainless steel is being good intermediate. Then if you look at the thermal conductivity, cupronickel is offering very good thermal conductivity where 29 watt per millikelvin. Then we have next to it is stainless steel. Then we have titanium. In terms of cost, stainless steel is relatively cheaper than cupronickel, and when we compare it with titanium, is that stainless steel is very cheap. Titanium is being costlier, and stainless steel is being relatively less costly. So cupronickel win for its marine thermal systems, particularly where it offers very good seawater resistance as well as it offers very good thermal conductivity. Whereas and it is basically offers a balanced performance and cost in terms of its strength as well as cost, particularly when it is being compared with titanium. If you see the failure modes and its prevention, so erosion corrosion is a problem where the solution could be we have to maintain the flow velocity that is less than 3 meter per second in the pipes, so that the corrosion resistance can be avoided, the problem of erosion can be avoided. Then we have sulfide attack, that is hydrogen sulfide in the polluted harbors where high amount of nickel grades are getting used. Then corrosion, corrosive corrosion, so this can be avoided basically the stagnated water and the proper gasket design. If we have a proper gasket design and if we can avoid the stagnation of the water, so this kind of problem, crevice corrosion can be eliminated. So these are some of the failure modes and the preventions that are given. So one is erosion is a problem, then sulfide attack, then this corrosion, crevice corrosion, and its preventions are also we have discussed it. Then if you see the summary overall, the key takeaways. So where nickel is being in the cupronickel, nickel is being added at 10 to 30%. In addition to that, we are also adding iron and manganese, which gives the ultimate marine alloy for us. In the microstructure, we can see single phase alpha solids or alpha structure, which enables cold working strengthening mechanisms. And the cost performance balance makes it irreplaceable in ships and desalination plants. So if you wanted to remove the salt, that desalination plants as well as in the ships, this offers a balanced cost performance material. So from coins to aircraft carriers, cupronickel are being used in cupronickel keep the world's salt water at bay. One can say that. It finds its applications from coins to its aircraft carriers. So cupronickel finds its applications uh, in marine particularly. So I have followed these references for making these content slides. And a question to ponder the audiences: why not use titanium everywhere if it's more corrosion resistance? We have seen the property differences comparisons, so you can ponder on this. You can reply in the chat. Why not use titanium everywhere if it's more corrosion resistance? Hint is also given here, so it's a cost and conductivity trade-off. So we have also in our slides we have also discussed about it. Right. So that's all for this today's class. In our next class, we will discuss another material. Thank you.